So I'm doing this same process where I am comparing my series to the function just 1 over x. I got this function 1 over root x. I got this function from taking the formula out of my series and treating the variable as an arbitrary real number instead of just a whole number. And this time, what happens? Well, I know that this series has to be greater than or equal to the value of this integral, but this integral diverges. So if I was going to do my improper integral here, right, I would need to look at a finite interval, and I would take my antiderivative and try to evaluate it there. But in the limit, this improper integral diverges. So the series also has to diverge. Now, I want to get a little bit more technical than that. These two observations we've made here, so with the series that converges and the series that diverges, there is a formal test that we can use. And there are two different versions of it. So this is called the integral test. So this has to do with series whose summands follow a formula, and that formula is defined for all real numbers, or at least all real numbers greater than or equal to 1. And this fits a lot of series that we end up looking at. So what we're going to do in both versions of this is we're going to take that formula from our series. So let's say I had, say, a summation of 1 divided by n to the power 6. How do I know whether this sum converges or diverges? Well, I am going to compare it to this integral instead, where I change my integral to 1 divided by x to the power 6, dx. I integrate starting at x equals 1. I go to infinity. Again, this is an improper integral. And all I'm doing is I check, is my integral convergent or divergent? Now, in this example, this integral does converge, which means that my original series converges as well. So this is a convergent series. If I do this process and my integral diverges, then the original series that I took this from also diverges. So whatever this improper integral does, so does the series. Now, the trick that made this all work was the fact that I could draw those rectangles either above or below the curve of the function. So it's really important here that the function f has to satisfy 3 different properties. Number 1, the function has to be continuous. That's how I know I can take an integral. The function has to be positive. That's how I know that I can have the area above the x-axis. And the function has to be decreasing, right? So that's not such a stringent requirement. I know that terms in my series need to be shrinking in absolute value to make sure that, as a prerequisite for the series to converge. So if you have all 3 of these things, then the integral test is yours for whatever tool you need it to be.